Imagine spending your entire life building a monument, watching it become the absolute foundation of modern science, and then spending the next 2 decades trying to tear it down because the universe refuses to cooperate with your blueprint. This is the reality for Adam Riess, a physicist who climbed to the absolute peak of scientific achievement, captured a Nobel Prize, and now finds himself staring at a set of numbers that simply should not exist. The very cosmos he helped map appears to be breaking the rules we wrote for it. We are facing a grand cosmetic divergence, two flawless measurements of our universe yielding two entirely different answers, and the most sophisticated space telescope ever constructed has just confirmed that neither side made a mistake. What we are witnessing are the literal fault lines of reality, a mysterious cosmic force that might be changing its behavior, galaxies that seem to have populated the deep past far too quickly, and an overarching cosmic architecture that looks increasingly asymmetric. If you have ever wanted to peer into the moments where human certainty crumbles and gives way to genuine mystery, this is your invitation to settle in, shed your assumptions, and question everything you think you know about space and time. In a quiet, unassuming office located at Johns Hopkins University in Baltimore, a scientist is looking at data that defies the laws of physics as we know them. Adam Riess isn't a fringe theorist or a contrarian seeking attention. He is one of the most celebrated and decorated scientific minds alive today. Back in 2011, he stood on a stage in Stockholm to receive the Nobel Prize in Physics for a discovery that shocked the global scientific community. The revelation that the universe isn't just expanding, but that it is flying apart faster and faster with every passing second. It was a revelation so profoundly disruptive that it literally forced publishers to rewrite every astronomy textbook on the planet. That single discovery became the absolute bedrock of what modern researchers call the standard model of cosmology. This model is the ultimate mathematical biography of existence, a master framework designed to explain precisely how our universe exploded into being, how it organized its vast networks of galaxies, and how it will eventually meet its ultimate demise. Because Riess himself poured the concrete for this conceptual foundation, you would expect him to be its fiercest protector. Instead, he has transformed into its most formidable challenger. For well over 10 years, Riess has been probing the deep structures of space with a level of precision that previous generations of astronomers could only dream of. Yet, the cleaner his data becomes, the more problematic the universe appears. He has openly observed that something smells fundamentally wrong with our master blueprint, noting that the empirical numbers returning from the depths of the sky flatly refuse to align with the rigid demands of the theory. Consider the sheer psychological weight of this situation. Imagine an engineer who designs a magnificent, record-breaking skyscraper, wins every architectural award in existence for its creation, and then, years down the road, notices a profound structural fracture running right through the building's central pillar. The natural human instinct might be to look away, to minimize the flaw, or to blame the shifting ground. Riess did the exact opposite. He walked straight toward the fracture, magnifying glass in hand. His peers in the field often describe him as absolutely relentless, possessing a fiercely competitive edge and a willingness to debate anyone who tries to casually sweep his data under the rug. There are certainly senior researchers who argue that he is jumping the gun, maintaining a firm and respectable stance that these strange discrepancies will eventually evaporate once our instruments become even more refined. That is a completely fair and honest scientific position. But what makes the current situation so compelling is that Riess has spent years actively trying to make his own revolutionary results disappear. He has tested his methods from every conceivable angle, and stress-tested his algorithms, and willingly handed his raw datasets over to his direct professional rivals, practically begging them to find the flaw he might have missed. No one has found it. To appreciate exactly why the scientific community is losing its collective sleep over this, we have to understand the staggering scale of what is currently hanging in the balance. The standard model of cosmology doesn't just look backward to explain history. It acts as an oracle that dictates the ultimate fate of every single thing in existence. It tells us what will happen to the furthest superclusters of galaxies, the nearest stars, the planet beneath our feet, and every individual atom inside your body over the course of trillions of years. If this mathematical model is fundamentally flawed, then the grand narrative of how the universe ends is completely wrong. The destiny we were all taught to accept, a slow, agonizing fade into a perfectly cold, dark, and utterly silent void, might be nothing more than a piece of scientific fiction. Riess has occasionally shared a deeply moving, almost haunting thought about his current position. He sometimes feels as though he is merely collecting loose crumbs of evidence, killing time while waiting for a new Einstein to finally emerge from obscurity and make sense of the chaos. Think about that for a second. A Nobel laureate operating at the absolute frontier of human intelligence, openly admitting that the current mystery might require a level of genius that hasn't even been born on this planet yet. That is the true depth of the cosmic abyss we are staring into. To trace the origins of this crisis, we have to journey back to the late 1990s. We have to look at a younger version of Riess, working late into the night, running a calculation that seemed so completely impossible that he assumed it was a catastrophic error. What he discovered during those lonely hours didn't just win him physics' highest honor, it planted the exact conceptual explosive that now threatens to bring down the entire palace of modern cosmology. And the most brilliant twist of all is that the historic discovery that made his career and the terrifying mismatch that currently keeps him awake at night are likely just two different sides of the exact same hidden truth. Picture the scene. It is the late 1990s, and a young astronomer is hunched over a glowing computer monitor in the pitch black, running the exact same analytical pipeline for the 10th time because he cannot believe what his screen is telling him. Riess was deeply immersed in studying incredibly distant, cataclysmic stellar explosions known as supernovae, and his spreadsheets were spitting out absolute nonsense. At that specific moment in human history, there was a universal consensus across the global scientific establishment. Everyone agreed on a beautiful, intuitive narrative. The universe burst into existence during the Big Bang. It had been expanding outward in all directions ever since. The collective gravitational pull of all the matter in the cosmos was acting as a cosmic brake pedal, gradually slowing that expansion down over time. It made perfect intuitive sense. If you throw a baseball straight up into the air, the gravitational pull of the Earth immediately begins to fight against the ball's upward momentum, dragging its speed down until it stops and returns to the ground. The only real question left for astronomers to answer was exactly how fast the cosmic expansion was slowing down. That was the explicit mission that Riess and his colleagues set out to accomplish. To achieve this, they relied on a highly specialized category of dying stars known as Type Ia supernova. In the astronomical community, these celestial events are prized as standard candles. Because these specific stars always explode with an incredibly uniform, predictable intrinsic brightness, they act as cosmic light bulbs of a known wattage. If you know exactly how bright a light bulb truly is, you can calculate precisely how far away it is simply by measuring how dim its light appears by the time it reaches your eyes. It is the exact same mental calculation you perform when you are driving down a dark country road at night and estimate the distance of an oncoming vehicle based on the faintness of its headlights. Riess meticulously observed dozens of these blinding cosmic detonations, tracking explosions so unbelievably remote that their light had been traveling through the empty void of space for billions of years before finally colliding with the mirrors of his telescopes. He mapped their true distances and compared those metrics against the physical speed at which they were fleeing away from us. The cosmos was supposed to be losing momentum. Instead, the data showed that it was rocketing outward. Riess's immediate reaction wasn't triumph, it was panic. He assumed he had committed a basic mathematical blunder. Perhaps he had flipped a negative sign in a dense equation, introduced a critical bug into his software code, or allowed a contaminated observation to poison the broader dataset. He completely dismantled his own analysis, hunting for the ghost in his machine, but the error refused to manifest. Meanwhile, entirely independent of his efforts, a fierce rival team of astronomers led by Saul Perlmutter was tracking their own set of distant supernovae using completely different methodologies and distinct observational techniques. They ran their numbers, looked at their screens, and hit the exact same impossible wall. Two fiercely competitive teams racing toward a historic finish line had accidentally stumbled upon the exact same forbidden answer. The expansion of our universe isn't slowing down at all. It is accelerating. Something deeply mysterious is actively pushing every single galaxy away from every other galaxy, and the strength of this repulsive push actually intensifies as the fabric space itself stretches out. Lacking any clear understanding of what this invisible force could possibly be, scientists gave it a vague, mysterious placeholder name: dark energy. To truly internalize how deeply surreal this discovery was, return to the baseball analogy. Imagine tossing a baseball up into the sky, watching it rise, slow down slightly as it fights gravity, and then, instead of falling back down, suddenly igniting like a SpaceX rocket, accelerating upward into the stratosphere, moving faster and faster every single second, as if some invisible hand had grabbed it and hurled it into the deep void. That is precisely what the universe is doing, with entire clusters of galaxies containing trillions of stars. The revelation hit the scientific world like a massive tectonic shift. Within a matter of years, independent observations confirmed the reality of the acceleration. And in 2011, Adam Riess, Saul Perlmutter, and Brian Schmidt stood together to accept the Nobel Prize. Dark energy was officially coded into the definitive equations of modern physics, transformed into an unshakable pillar of the Standard Model. Yet, if you look closely at that pillar, you realize it is built entirely out of pure, unadulterated mystery. To this very day, we have mountains of empirical data confirming that dark energy is actively operating out there in the dark, but we have absolutely zero physical experiments that can tell us what it actually is. It is a ghost in our mathematical equations, a name we invented to mask our profound ignorance. When Riess and his peers sat down to calculate the definitive cosmic inventory of our universe based on these new dynamics, the results they came back with were deeply humbling. The sheer rate of the cosmic acceleration meant that this unknown invisible force didn't just exist. It completely dominated the cosmic landscape, utterly overwhelming the gravitational influence of everything we can actually see by a staggering margin. Every burning star, every orbiting planet, every sweeping galaxy, and every single atom that has ever been observed through a lens or captured by a sensor turned out to be nothing more than a minor cosmic ingredient in a universe completely controlled by the unseen. The true proportions of our reality are deeply startling, revealing that everything we have ever encountered is barely a historical footnote in the ultimate accounting of nature. Hold your hand out in front of your face right now and look at it. Think about the complex arrangement of skin, bone, blood, and muscle, all of it composed of heavy atoms that were forged billions of years ago inside the crushing thermonuclear hearts of ancient dying stars. Now, accept this verified scientific reality. Everything in existence made of normal atoms adds up to a meager 5% of the total universe. The remaining 95% of reality is completely invisible to us. It has never been physically touched, it has never been trapped in a laboratory, and it has never been directly registered by a single scientific instrument ever constructed by human hands. Astronomers divide this massive, invisible empire into two distinct components. Dark matter, approx 25%, an unseen, unidentified substance whose immense gravitational grip acts as the structural scaffolding of the universe, holding massive galaxies together. We are certain it exists because galaxies spin around at such an intense velocity that if they relied solely on the gravity of their visible stars, they would violently tear themselves apart, flinging their components out into the void, like water droplets flying off a rapidly spinning bicycle wheel. Something massive is holding them together, outnumbering visible matter 5-1, yet it refuses to emit light, heat, or any detectable electromagnetic signal. Dark energy, approx 70%, the repulsive force discovered by Riess and his colleagues. It operates as the exact opposite of dark matter. Instead of pulling structures together, it works tirelessly to drive the very fabric of space apart. To visualize this incredible imbalance, imagine the entirety of the cosmos as a large 20-slice pizza. Every single thing astronomy has ever cataloged, every glittering star, every sweeping spiral galaxy, every glowing nebula, and every pixel of every breathtaking image ever captured by the Hubble or James Webb telescopes fits neatly onto one single slice. The other 19 slices are entirely dark, hidden, and completely unexplained. That is the baseline of human understanding. To be perfectly precise about where our trust lies, the physical existence of these dark components isn't in doubt. It is backed up by an array of independent observational vectors. The science confirming their presence is rock solid, but their fundamental identities remain completely blank. For generations, particle physicists have hunted for dark matter using massive, highly sophisticated detectors buried deep underground in abandoned mine shafts, shielding tanks of liquid, noble gases cooled down to absolute zero, waiting for a single, invisible cosmic particle to crash into an atomic nucleus. The detectors have steadily grown large enough to capture almost anything, yet the silence from the deep Earth remains absolute. Dark energy is an even more frustrating enigma. It behaves as an intrinsic property of empty space itself, implying that even a perfect vacuum of absolute nothingness contains a native, unyielding charge that pushes outward against the rest of the cosmos. When quantum physicists attempted to calculate exactly how powerful this vacuum push ought to be, using the rules of quantum field theory, the answer they derived was so spectacularly wrong that it is widely considered the single most catastrophic prediction in the history of science. The theoretical calculation and the actual astronomical measurements miss each other by a factor of 10 to the 120th power, a 1 followed by 120 zeros. This is why this mismatch matters so deeply for the story of Adam Riess. Our finest theory of the very small, quantum mechanics, and our finest theory of the very large, general relativity, when brought together to answer a fundamental question about the nature of space, break down completely. The standard model of cosmology is built directly on top of these twin mysteries. It operates on two foundational assumptions. It assumes that dark matter behaves in a simple, predictable way, and it assumes that dark energy is perfectly uniform and constant, never altering its strength from the dawn of time until the absolute end of existence. For 20 years, these basic assumptions worked beautifully, allowing scientists to fit thousands of independent observations into a single cohesive worldview. But an assumption is ultimately just a theoretical promise, waiting for an instrument precise enough to test its validity. Riess spent his entire career creating the exact tools capable of executing that test. Before we watch the model fracture, we need to understand exactly what the standard model of cosmology is and why the scientific community placed such absolute, unwavering faith in it. Think of it as a comprehensive biography of our universe written in the language of pure mathematics. The story opens nearly 14 billion years ago with the Big Bang, an unfathomably hot, dense singularity. In the first unimaginable fraction of a second, the model dictates that space experienced a period of violent, faster-than-light expansion known as inflation, smoothing out the fabric of the young cosmos like a crumpled bedsheet snapped completely flat. As the system expanded and cooled down, fundamental particles coalesced, creating the first simple atoms, and light finally broke free from the dense primal plasma, traveling outward into the void. Over deep time, gravity went to work, gathering matter into complex webs, knots, and filaments. Those dense knots eventually ignited to form the first generations of stars. Stars organized themselves into massive galaxies, and galaxies clustered together along invisible highways of dark matter, constructing a vast cosmic web that spans everything we can observe today. The most elegant aspect of this model is that it requires only a tiny handful of fundamental parameters to explain this vast, sweeping history. A specific amount of ordinary matter, a generous allocation of invisible dark matter, a dominant, unvarying quantity of dark energy that remains constant forever. When you plug these simple ingredients into the gravitational equations outlined by Albert Einstein, the history of the universe unfolds across a supercomputer screen with breathtaking accuracy, mimicking the real-world cosmos almost perfectly. The historical successes of this model are undeniably brilliant. It predicted the exact, hyper-precise pattern of tiny hot and cold fluctuations in the ancient radiation left over from the Big Bang, And when advanced satellites mapped that radiation, the real-world data matched the mathematical prediction with staggering fidelity. It calculated the precise amounts of light chemical elements like hydrogen and helium that should have been cooked up in the primordial furnace of the early universe, and our chemical measurements matched those ratios to the decimal point. It even mapped out exactly how galaxies should be clustered across the sky, and massive robotic sky surveys found those exact geometric distributions. For 2 decades, the Standard Model was the undisputed detective story of the cosmos, a single theory that cleanly explained every clue on every page. It became the mandatory matrix through which every new astronomical discovery had to be interpreted. Massive academic careers were built entirely within its boundaries. Textbooks enshrined its equations as absolute truth, and some researchers even began to speak as if the future of cosmology was nothing more than an uninspiring exercise in cleaning up decimal places. Crucially, the model also gave us our definitive ending. If you run its equations forward into the deep future, the outcome is stark and undeniable. Dark energy, acting as an immutable constant of nature, will continue to drive the expansion of space faster and faster. Over vast spans of time, distant galaxies will be accelerated away from us so quickly that their light will no longer be able to bridge the widening chasm, vanishing entirely from our night sky. Star formation will completely sputter out as the cosmic reservoirs of hydrogen gas run completely dry. The final generations of stars will cool down into dark, lifeless cinders, leaving the cosmos to end in a state of absolute cold, black, and completely empty nothingness. But remember the critical point. The model's description of the distant past is verified by empirical evidence, but its description of our ultimate future rests entirely upon that single, massive assumption that dark energy never changes its behavior. Every single prediction about the fate of reality hangs from that lone conceptual thread. For a generation, no instrument could test that thread. The model seemed completely invincible until the universe refused to agree on its most important number. Every great paradigm shift in human history begins with a stubborn, quiet disagreement. This particular crisis centers around the expansion rate of the universe, a value known to physicists as the Hubble constant. It is the definitive speed limit of the cosmos, telling us exactly how fast the fabric of space is stretching right now, tonight, while you read these words. If you can measure this number with perfect accuracy, you immediately unlock the true age of the universe, its absolute physical scale, and its ultimate destiny. If you get it wrong, every single calculation in astrophysics drifts completely off course. There are 2 primary methods for measuring this constant, and this is where the entire foundation of modern cosmology splinters in 2. The first approach focuses entirely on the modern universe, the space immediately surrounding our cosmic neighborhood. Astronomers like Adam Riess use advanced telescopes to measure the precise distances to nearby galaxies and clock exactly how fast they are racing away from us. By combining distance and velocity, they can read the expansion rate directly. It is the cosmic equivalent of a police officer standing on the side of a highway with a radar gun, registering the speed of passing vehicles in real time. The second approach takes the opposite route, focusing entirely on the ancient universe. Scientists use highly sensitive satellites to map the cosmic microwave background, the faint, primordial afterglow of the Big Bang released when the universe was in its absolute infancy. They analyze the structural patterns of this ancient light with extreme precision, plug those parameters into the equations of the Standard Model, and allow the mathematics to run forward across 14 billion years of history. It is like carefully winding up a mechanical clock at the dawn of time and letting it tick forward to the present day to see what time it reads now. If the Standard Model is an accurate description of reality, these 2 distinct methods must yield the exact same number. But they don't. The radar gun method, looking at the universe right around us, consistently clocks the expansion rate at a value roughly 9% faster than the projection, calculated by winding the ancient cosmic clock forward. A 9% variance might sound like a trivial rounding error, but in the hyper-precise world of modern cosmology, it represents a massive, unbridgeable canyon. Over the years, both competing camps have relentlessly sharpened their analyses, but instead of merging closer together, The two answers have hardened into immovable walls, each becoming more certain and more incompatible with the other. This persistent mathematical standoff has been named the Hubble tension. Think of it this way. Imagine two legendary world-renowned watchmakers who are tasked with evaluating the health of a patient. One watchmaker meticulously examines the patient's official birth certificate, tracking every historical record from the day they were born. The other watchmaker puts a high-tech stethoscope up to the patient's chest to check their pulse right now. The birth certificate insists that the patient ought to have a calm, resting heart rate of 67 beats per minute. The stethoscope clearly reports that the heart is racing at 73 beats per minute. Both watchmakers verify their equipment 1,000 times, and both audits come back completely clean. Someone has to be wrong. And if neither measurement contains a mistake, then the mathematical bridge linking the past to the present, the standard model itself, is missing a fundamental piece of reality. Because Adam Riess has completely staked his immense scientific reputation on his team's measurements being absolutely flawless, it is vital to understand why he feels such total confidence. His side of the argument is built upon a towering interconnected scaffolding of empirical evidence that astronomers refer to as the cosmic distance ladder. You cannot simply stretch a physical tape measure across the empty void of space to find out how far away a galaxy is. Instead, astronomers have constructed a chain of overlapping observational methodologies where each individual rung of the ladder is used to calibrate the accuracy of the rung immediately above it. The very first rung of this ladder begins right on our cosmic doorstep, using pure, unadulterated geometry. As the Earth completes its annual orbit around the Sun, nearby stars appear to shift their physical positions ever so slightly against the background of incredibly distant galaxies. It is the exact same optical effect you experience when you hold your thumb out in front of your face and blink your left eye, then your right eye. Your thumb appears to jump back and forth against the wall behind it. By measuring that tiny angle of displacement with extreme precision, basic high school trigonometry hands you the absolute distance to that star. The second rung climbs higher by utilizing a unique class of pulsing stars known as Cepheid variables. These massive stars naturally brighten and dim in a remarkably predictable rhythmic cycle. More than a century ago, a brilliant astronomer named Henrietta Leavitt discovered a fundamental law of nature. The slower a Cepheid variable pulses, the inherently brighter it truly is. This means that by simply timing the rhythm of a Cepheid's pulse, you can immediately determine its true wattage. By comparing that known true brightness against how dim the star actually appears from Earth, you can calculate its exact distance, much like judging the distance of a distant lighthouse out at sea when you know the precise power of its bulb. The geometric measurements from the first rung are used to calibrate the Cepheids, allowing astronomers to extend their tape measure out into neighboring galaxies millions of light years away. Finally, in some of those distant galaxies containing Cepheids, astronomers are lucky enough to catch the third rung of the ladder, type Ia supernovae. These exploding stars are so spectacularly brilliant that a single detonation can briefly outshine an entire galaxy composed of 100 billion suns, making them visible across billions of light years. The Cepheids are used to calibrate the true brightness of the supernovae, and those supernovae are then used to reach across the deepest expanses of the expanding universe, allowing astronomers to read the modern expansion rate directly from the fabric of space. The structural weakness of this ladder is completely obvious, and Riess understood it better than anyone. If a single error creeps into any individual rung, that mistake will climb upward, poisoning every single calculation above it. For years, critics focused their attacks on the second rung, arguing that the Cepheid measurements were inherently contaminated by a phenomenon known as crowding. Cepheids naturally tend to live in incredibly dense, dust-choked star-forming regions. When older space telescopes photographed them from millions of light years away, the light from neighboring stars would frequently blend into the image, creating a blurry, smeared blob that made the Cepheids appear subtly brighter than they actually were. It was a completely valid, deeply serious scientific objection. So Riess and his team attacked their own life's work. They swapped out their targets, utilized different wavelengths of light that could slice through cosmic dust, and completely replaced Cepheids with entirely different categories of stellar rulers. Yet, no matter how many times they rebuilt the ladder from scratch, the fast expansion rate refused to change. Still, one final skeptical loophole remained. The images were just slightly too blurry to completely rule out crowding. The entire field needed an instrument with an eye sharp enough to resolve those pulsing stars cleanly, one by one, across the great intergalactic ocean. At the tail end of 2021, that exact instrument was launched into space. The James Webb Space Telescope was about to deliver an absolute verdict. To understand the sheer drama of that moment, we must also look across the battlefield at the rival measurement, which is just as formidable. The camp that derives the slower expansion rate extracts its data from the oldest light in existence, the cosmic microwave background. When the universe was in its infancy, it was an incredibly dense, opaque soup of plasma, so intensely hot that light could not travel through it. Photons were constantly colliding with free electrons, trapped in a permanent cosmic fog. But roughly 380,000 years after the Big Bang, the universe cooled down to a point where protons and electrons could finally bind together to form the very first stable hydrogen atoms. In an instant, the cosmic fog cleared and the primary light of creation broke completely free, rushing outward in every direction at once. That ancient flash of light has been traveling through space for nearly 14 billion years. Tonight, it completely fills the entire sky, though cosmic expansion has stretched its wavelengths down into the invisible microwave spectrum. It is the absolute baby picture of our cosmos. When modern satellites map this primordial afterglow, they revealed that it is speckled with incredibly subtle hot and cold spots, tiny fluctuations in temperature that vary by less than 100,000th of a degree. These minute ripples are the absolute seeds of our modern reality. Every dense patch of that ancient plasma would eventually collapse under the relentless pull of gravity to form the vast networks of galaxies, stars, and planets we see today. You are physically alive right now because of a tiny ripple in that ancient cosmic soup. By analyzing the precise geometric sizes and distributions of those speckles, scientists can reverse engineer the exact chemical recipe of the infant universe, determining precisely how much dark matter and dark energy it contained. When they feed that pristine recipe into the standard model and let the equations run forward through time, the model outputs a hyper-precise value for what the expansion rate should be today. The internal consistency of this method has been verified in thousands of ways, and the answer it delivers is stubbornly low. To see this clash clearly, imagine finding a photograph of a wild mountain river taken near its source, high up in the peaks, long ago. The photograph is so spectacularly detailed that hydraulic engineers can calculate exactly how fast that water ought to be rushing past a specific valley downstream today. But when you walk down to that valley, drop a physical leaf into the current, and time it with a stopwatch, you discover that the water is moving substantially faster than the historical photograph allows. You check the photograph. It is flawless. You check your stopwatch. It works perfectly. Both cannot be simultaneously correct unless something fundamental altered the nature of the river as it flowed down the mountain. If both datasets are clean, the mathematical bridge linking them is broken. The standard model is missing something major. For years, mainstream cosmology clung to the comforting hope that the distance ladder was simply wrong, that those blurry, crowded Cepheids were hiding a systematic human error. Then, the James Webb Space Telescope opened its massive, golden hexagonal mirror 1,000,000 miles from Earth. Operating in permanent shadow at temperatures near absolute zero, it aimed its pristine infrared optics directly at the exact stars Riess had spent his life tracking. If the critics were right, Webb's vastly superior resolution would cleanly separate the Cepheids from their crowded neighbors, revealing them to be dimmer than previously thought. The distance calculations would shift, the local expansion rate would drop, the tension would vanish, and the standard model would be saved. The data came back. The verdict was absolute. Webb's razor-sharp infrared observations matched the older Hubble Space Telescope measurements almost perfectly. The stellar crowding had introduced no meaningful error whatsoever. The distance ladder was true. The fast expansion rate was a real physical fact of the modern universe. Riess and his colleagues pushed even further, systematically replacing every single controversial rung of their ladder with pristine data captured by the new telescope. The number refused to budge. The nearby universe really is flying apart roughly 9% faster than the early universe architecture demands. This was the exact moment the conversation changed forever. The Hubble tension was no longer an annoying anomaly that could be casually brushed aside as a measurement error. It had been certified by the most advanced piece of observational technology ever built by the human race. The escape hatches were slammed shut. With experimental error effectively ruled out, the scientific community had to face a deeply unsettling reality. We have fundamentally misunderstood the universe. To see how comprehensively the team defended their results, look at the staggering list of alternative explanations they systematically hunted down and eliminated over the years. Cosmic dust. Critics suggested that interstellar dust clouds were dimming and reddening the starlight, throwing off the distance calculations. The team bypassed this by measuring the entire ladder in infrared light, which glides through cosmic dust as easily as sound waves travel through a drywall partition. The fast expansion rate held. Stellar chemistry. Skeptics hypothesized that Cepheid variables in distant ancient galaxies might possess a different chemical makeup than those nearby, altering their pulsing rhythms. The team cross-tested Cepheids across a vast array of galaxies with wildly varying chemical compositions. The fast expansion rate held. Alternative stellar rulers. To rule out any native flaws unique to the entire species of Cepheid stars, astronomers completely rebuilt the distance ladder using a totally different class of stars known as red giants, whose maximum brightness is governed by completely different, pristine nuclear physics. The fast expansion rate held. Human bias. To eliminate the subtle danger of scientists subconsciously steering their data toward a preferred conclusion, multiple independent teams executed fully blinded analyses, masking the final numbers from their own views until the software code and data selection choices were completely locked in stone. The fast expansion rate still held. Bypassing starlight entirely. In an astonishing feat of radio astronomy, researchers mapped the geometric orbits of massive water vapor clouds directly circling the supermassive black holes at the centers of distant galaxies. This technique allowed them to calculate absolute distances using pure geometry in a single leap, completely bypassing stars, dust, and the distance ladder altogether. The result agreed perfectly with the fast expansion rate. We are left standing on the edge of a genuine scientific revolution. The blueprint we trusted for decades is fractured, and the universe is telling us that our work is far from finished. The story of cosmology isn't coming to a close. It is opening a brand new, completely unwritten chapter. The realization that the cosmic distance ladder is structurally sound did more than just validate a decade of painstaking work by Adam Riess. It shattered the collective complacency of an entire discipline. For 20 years, cosmology had been operating in a state of relative tranquility, treating the standard model as an absolute truth. The verification of the Hubble tension transformed that tranquility into a chaotic rush for answers. When you eliminate the possibility of human error from a measurement of this scale, you are forced to confront the limits of your own theory. The discrepancy between the baby picture of the universe and its current pulse rate means that the story we have been telling ourselves about space and time is missing a fundamental chapter. The bridge is broken, and the crack is widening. To understand where cosmology goes from here, it helps to look at the sheer desperation of the theoretical ideas now flooding the scientific literature. When a beloved model begins to fracture, theorists do what they have always done. They start tinkering with the fundamental ingredients of reality. Every week, new papers are published proposing radical modifications to the laws of physics, each trying to find a way to make the universe expand just a little bit faster today, without ruining the beautiful alignment we see in the ancient past. One of the most popular ideas currently being debated is a concept known as early dark energy. Remember that the standard model assumes dark energy is perfectly constant, a smooth, unvarying background hum that only begins to dominate the universe billions of years after the Big Bang. But what if dark energy isn't a static constant? What if it experienced a sudden, violent burst of strength when the universe was just a few 100,000 years old? Imagine the young universe as a vehicle coasting along a highway according to a strict schedule. If that vehicle suddenly encounters a hidden temporary surge of fuel, a brief tap on the accelerator pedal, it will jump ahead of its expected position. If you are an engineer looking only at the starting line and the finish line, you will be baffled by how fast the vehicle arrived at its destination. By introducing a temporary burst of dark energy into the early universe, theorists can effectively give the young cosmos a quick kick, accelerating its expansion just enough to match the fast radar gun measurements we see today. Once its job is done, this early dark energy would have to vanish completely, fading into the background so it doesn't disrupt the rest of cosmic history. It is an elegant mathematical trick, but it leaves experimental physicists with a deeply unsettling question. What kind of force simply blinks into existence for a brief cosmic moment and then disappears without leaving a trace? Other researchers are looking closely at the other major mystery of the cosmic inventory: dark matter. The Standard Model treats dark matter as completely cold and inert, invisible particles that interact with the rest of the universe through gravity and nothing else. But as the crisis deepens, scientists are beginning to wonder if dark matter might possess hidden properties. What if dark matter particles are not entirely stable? If dark matter slowly decays into dark energy over billions of years, the cosmic balance of power would shift over time. As the invisible scaffolding of dark matter dissolves, the repulsive push of dark energy would grow stronger, causing the modern universe to fly apart at an accelerated rate that the ancient baby picture could never have predicted. Alternatively, some models suggest that dark matter might actively interact with the relic radiation of the Big Bang, creating a subtle dragging effect in the early universe that alters our interpretation of the cosmic microwave background. The moment you allow these dark components to talk to each other, the equations become wildly complex, and the clean, simple universe of the Standard Model dissolves into a chaotic web of invisible interactions. The most radical thinkers in the field are aiming their conceptual weapons at the most sacred cow of all: Albert Einstein's theory of general relativity. For over a century, general relativity has served as the undisputed law of gravity, passing every experimental test humans have ever thrown at it, from the bending of starlight around the sun to the detection of gravitational waves from colliding black holes. But all of our direct, high-precision tests of Einstein's gravity have been conducted within the relatively small confines of our solar system or our immediate stellar neighborhood. What if gravity changes its behavior when stretched across billions of light years of empty space? If gravity grows subtly weaker on the largest cosmic scales, the cosmic web would hold on to the expanding universe with a looser grip, allowing space to stretch out faster today than our standard equations predict. Modifying Einstein's equations is a dangerous game. Change a single variable to fix the expansion rate, and you risk completely ruining the model's ability to explain how galaxies formed in the first place. Yet, such is the depth of the current crisis that even Einstein is no longer off limits. As if the Hubble tension weren't enough to push cosmology into a state of panic, the plot thickened significantly as the mid-2020s progressed. For a long time, defenders of the Standard Model could argue that the expansion rate mismatch was an isolated anomaly, a single weird result that didn't necessarily mean the whole structure was garbage. But as our telescopes have grown more powerful, entirely new cracks have begun to appear in completely different parts of the cosmic architecture. The most spectacular of these new challenges came from the James Webb Space Telescope itself, shortly after it finished verifying Adam Riess's distance ladder. When Webb peered deeper into the dark void than any instrument in history, it effectively looked back in time, capturing light that left the first galaxies just a few 100 million years after the Big Bang. According to the Standard Model, the early universe should have been a relatively quiet, unorganized place. Gravity takes time to gather massive clouds of gas together and ignite them into stars. The first galaxies were supposed to be small, chaotic, and sparse. Webb looked into the deep past and found something entirely different, It discovered massive, highly organized, brightly shining galaxies existing at a time when the universe was in its absolute infancy. Some of these ancient cosmic structures appeared to contain as many stars as our modern Milky Way, packed into the universe's earliest epochs. To understand how shocking this is, imagine walking into a nursery, looking into a crib, and finding a fully grown, bearded man sitting where a newborn baby is supposed to be. It completely defies the biological timeline of human growth. In the exact same way, these impossible early galaxies completely defy the cosmological timeline of structural growth laid out by the Standard Model. There simply shouldn't have been enough time for gravity to harvest that much matter and construct such massive galactic engines so early in history. At the same time, another independent observational crisis has been quietly gathering momentum. Astronomers call it the S8 tension, and it focuses not on how fast the universe is expanding, but on how smoothly its matter is distributed. By using massive telescopes to map out how the light from distant galaxies is subtly bent by the gravity of intervening dark matter, a technique known as cosmic shear, scientists can calculate exactly how clumpy or smooth the cosmic web is today. They can then compare this modern clumpiness against the prediction generated by the ancient baby picture of the universe. Just like the Hubble tension, the two methods refuse to agree. The modern observations consistently reveal that the universe is roughly 10% smoother and less clumpy than the Standard Model predicts it should be. If you wind the clock forward from the Big Bang, gravity is supposed to pull matter together into dense, tightly packed knots over time. But the real-world universe looks strangely diffuse, as if some unknown physical process is actively preventing gravity from gathering matter into the dense cosmic filaments the theory demands. When you sit back and look at the broader landscape of modern astronomy, you realize the situation has become critical. We have a universe that is expanding too fast, matter that is refusing to clump together properly, and massive galaxies that manage to build themselves far too early in history. These are no longer isolated anomalies. The cracks are beginning to connect, forming a clear message from the night sky. Our master blueprint is fundamentally incomplete. The reaction within the scientific community to this gathering storm has been a fascinating study in human psychology and the sociology of science. When a dominant paradigm is challenged, the response rarely consists of a sudden, clean surrender. Instead, fields fracture into distinct philosophical camps, each digging in its heels and defending its worldview with intense passion. In one camp stand the strict observational astronomers, the grease monkey scientists, who spend their lives dealing with the cold, hard realities of hardware, detectors, and raw data. For these researchers, the empirical results are paramount. They have spent a decade testing their instruments, characterizing their errors, and subjecting their pipelines to relentless peer review. From their perspective, if the data says the universe is expanding at 73 kilometers per second per megaparsec, then that is what the universe is doing, regardless of whether it makes the theorists' elegant equations look messy. They look at the Standard Model not as a sacred text, but as a working hypothesis that has finally met its match in the real world. In the opposing camp stand the classical cosmologists and theoretical physicists who spent their careers building and polishing the Standard Model. For them, the model's incredible track record of explaining the broader universe cannot be easily dismissed. They point out that the theory has successfully predicted the cosmic microwave background, the abundance of light elements, and the large-scale distribution of galaxies with jaw-dropping precision. To throw away a framework that's successful because of a few stubborn mismatches seems reckless. They remain convinced that some deeply hidden systematic error must be lurking somewhere within the local measurements. They suggest that perhaps our local region of the universe sits inside a massive, underdense void, a cosmic bubble that expands naturally faster than the broader background space. While this local void hypothesis has been largely ruled out by comprehensive galaxy counts, it represents the kind of conceptual lifelines defenders of the theory are willing to throw out to keep the Standard Model alive. This philosophical divide is exactly why the figure of Adam Riess is so uniquely compelling. He is not an outsider throwing rocks at the scientific establishment. He is a tenant of its highest offices. He understands the immense power of the Standard Model because his own Nobel Prize winning work is one of its core pillars. When he speaks about the cracks in the theory, he does so with a sense of profound responsibility rather than revolutionary glee. He has frequently noted that his goal was never to break cosmology, but to measure it with such absolute precision that the universe would be forced to reveal its deepest secrets. The relentless nature of this debate highlights a fundamental truth about how science actually progresses. True breakthroughs rarely happen when a scientist shouts "Eureka" in a moment of sudden inspiration. Real progress usually happens when a researcher looks at a clean data set, scratches their head in confusion, and mutters, "That's weird." It is the stubborn, unexplainable anomalies that drive us forward, forcing us to abandon our comfortable certainties and venture back into the unknown. The Hubble tension has dragged an entire generation of scientists out of their comfortable textbook assumptions and dropped them squarely back into a wilderness of pure discovery. As we look toward the horizon, the great cosmic standoff is about to be flooded with an unprecedented wave of new empirical data. The mid to late 2020s are shaping up to be a golden era for observational astronomy, with a fleet of next-generation observatories coming online, each explicitly designed to hunt down the missing pieces of our cosmic puzzle. One of the most highly anticipated assets is the European Space Agency's Euclid Space Telescope, alongside NASA's upcoming Nancy Grace Roman Space Telescope. Unlike the James Webb Space Telescope, which acts like a powerful magnifying glass focusing intently on tiny specific patches of the sky, these new observatories are designed to operate as wide-angle cameras. They will map out hundreds of millions of galaxies across immense swaths of the sky, charting the growth of the cosmic web across cosmic time with unprecedented fidelity. Simultaneously, on a remote mountain ridge in the Chilean Andes, the Vera C. Rubin Observatory is preparing to initiate its legacy survey of space and time. Equipped with the largest digital camera ever constructed for astronomy, the Rubin Observatory will photograph the entire available night sky every few nights, creating a massive, high-definition time-lapse movie of the dynamic cosmos. It is expected to discover millions of new Type Ia supernovae, expanding our local distance ladder dataset by orders of magnitude and completely overwhelming any remaining statistical uncertainties. These new tools will subject both sides of the Hubble tension to an unforgiving audit. They will map out the local expansion rate, the growth of cosmic clumpiness, and the emergence of early galaxies simultaneously. If the discrepancy is an illusion caused by some subtle, undiscovered quirk of our local galactic neighborhood, these vast surveys will expose it cleanly. But if the data holds firm, the sheer volume of new information will provide theorists with the precise clues they need to scrap the old assumptions and begin drafting a new, more comprehensive theory of the cosmos. We find ourselves standing in a deeply profound historical moment. It is easy to look at the current crisis in cosmology and feel a sense of disappointment, a feeling that the scientific establishment has failed us, or that the knowledge we thought was secure is suddenly slipping through our fingers. But that is a profound misinterpretation of what science actually is. Science is not a static catalog of established facts. It is an ongoing, adaptive process of building progressively better maps of reality. The fact that our best model of the universe is cracking under the weight of new data is not a defeat. It is a spectacular triumph of human ingenuity. It means our instruments have finally become so incredibly sharp and our measurements so breathtakingly precise that the universe can no longer hide its remaining secrets behind a wall of blurry data. We have pushed our understanding to its absolute limit, and the cosmos is responding by showing us that there is still so much more left to discover. Think back to the image of Adam Riess, sitting in his quiet office at Johns Hopkins University, looking at numbers that shouldn't exist. He is the ultimate personification of the scientific spirit, a man who won every accolade for helping to construct a beautiful picture of the universe, and who now possesses the courage to look that picture in the face and admit that it might be wrong. He isn't waiting for a comfortable consensus to protect his legacy. He is actively seeking the truth, even if that truth threatens to tear down the very monument he helped build. The Standard Model of cosmology served us brilliantly for a generation, providing a clean, elegant narrative of a universe born in fire, shaped by invisible dark components, and destined for a long, slow fade into the cold dark. But the night sky is whispering a different story tonight. It is telling us that dark energy might be dynamic, that gravity might be stranger than Einstein ever imagined, and that the ultimate fate of existence is still an open question. As the new observatories open their eyes and the data begins to pour in, we must be prepared to follow the evidence wherever it leads, to shed our oldest assumptions, and to embrace the wonderful, terrifying mystery of a universe that refuses to be neatly boxed into our textbooks. Settle in, keep looking up, and never stop questioning everything you know. The tension between the local distance ladder and the cosmic background has ceased to be an isolated puzzle. It is now the anchor point for a much larger systemic breakdown across the entire field of astrophysics. When you push the limits of precision, the universe doesn't just display minor errors. It begins to present entirely different versions of itself, depending on where and how you look. For the generations of scientists who built their careers on the absolute symmetry of the Standard Model, this realization has been an uncomfortable waking dream. The cracks have begun to spread from the expansion rate to the very structural components of the cosmic web, revealing that our mathematical description of reality is missing a core stabilizing mechanism. To understand how deep the conceptual restructuring must go, we have to look closely at the emerging ideas attempting to reconcile these two irreconcilable frameworks. Theorists are no longer just adjusting the knobs on the existing machinery. They are questioning whether the machinery itself was built on a series of fundamental misinterpretations. One of the most intensely scrutinized fields of study involves the concept of dark radiation. In the standard framework, the radiation budget of the early universe is tightly constrained by the known species of neutrinos, ghostly near-massless particles that flooded the cosmos during the first seconds after the Big Bang. But what if there are hidden, completely unmapped species of particles traveling through the dark? If the early universe contained an additional sterile variety of neutrino, one that does not interact via the weak nuclear force but still exerts gravitational influence, it would alter the expansion dynamics of the primordial plasma. Think of it like adding an invisible, highly volatile gas to a sealed pressure cooker. Even if you cannot see the gas, the internal pressure rises, forcing the container to expand outward against its environment with unexpected force. This extra dark radiation would naturally cause the infant cosmos to expand at an accelerated pace during its most formative era, shifting the baseline configuration of the speckles mapped by the Planck satellite. When you wind that modified clock forward, the predicted modern expansion rate naturally climbs, narrowing the canyon between the early universe calculations and the direct observations of Adam Riess. Yet, this solution introduces its own severe penalties. Sterile neutrinos or exotic relativistic particles would leave distinct, unmistakable fingerprints on the Big Bang afterglow, subtly altering the damping tail of the cosmic microwave background spectrum. As our instruments sweep across those data points with higher resolution, the room for such hidden particles is shrinking to a razor-thin margin, leaving theorists caught between a mathematical necessity and an uncooperative sky. Simultaneously, a parallel effort is underway to explore the bizarre possibility of dynamic dark energy, often referred to in theoretical circles as quintessence. For decades, the cosmological constant, symbolized by the Greek letter lambda, reigned supreme because of its sheer mathematical simplicity. It represents a perfectly uniform energy density inherent to the vacuum of space, never diluting as space expands and never changing its fundamental nature across cosmic epochs. But the stubborn resistance of the Hubble tension has forced scientists to dust off older, more complex equations where dark energy is treated not as a static property of the vacuum, but as a dynamic, evolving scalar field. If dark energy is dynamic, its behavior can change dramatically over the course of 14 billion years. It could have started as a weak, barely perceptible whisper in the ancient past, allowing gravity to cleanly aggregate matter into the seeds of our modern galaxies, before gradually shifting into a higher gear as the universe matured. This shifting of gears would naturally explain why the modern universe is rocketing apart at a pace that catches our historical models completely off guard. The implications of a dynamic scalar field are profound, completely upending our certainties about the long-term evolution of the cosmos. If dark energy can change its strength over time, it could just as easily reverse its direction in the distant future. The bleak, frozen scenario of the heat death is no longer a guaranteed certainty. If the scalar field decays or undergoes a phase transition trillions of years from now, the accelerated expansion could slow down, halt, or even invert into a catastrophic cosmic collapse, a final big crunch where space itself snaps back like a rubber band under tension. By attempting to solve a localized crisis in our modern measurements, we have inadvertently cast a shadow of absolute uncertainty over the ultimate fate of everything in existence. The complications multiply exponentially when you look at the real-world performance of these alternative frameworks against the broader backdrop of astronomical data. It is relatively easy to design a custom mathematical model that fixes the Hubble tension in isolation, but the universe is an intricately interconnected system. Every time a theorist alters an equation to accelerate the modern expansion rate, those changes ripple through the history of the cosmos, throwing other perfectly aligned pieces of the puzzle into complete disarray. This systemic resistance is most clearly visible when looking at the historical record written by baryon acoustic oscillations, BAO. These are massive, regular spherical imprints frozen into the distribution of galaxies across the sky, acting as a pristine cosmic ruler. They represent ancient sound waves that traveled through the hot pyroplasma of the early universe until the moment light broke free, locking the waves in place at a highly predictable physical scale. By measuring the sizes of these frozen sound horizons at various distances throughout cosmic history, astronomers have constructed an incredibly precise, continuous map of how the universe grew over billions of years. This map acts as an unyielding checkpoint for any new cosmological theory. If a scientist proposes an early dark energy model or a dynamic scalar field to resolve the Hubble tension, that new model must also pass through the BAO data without altering the distribution of these massive cosmic waves. Currently, the vast majority of exotic theories fail this test miserably. The real-world positions of these galactic rings act as a rigid straitjacket, consistently confirming that the universe has behaved with remarkable, predictable consistency throughout its Middle Ages. We are left with an agonizing paradox. The universe looks perfectly standard and well-behaved when mapped across its vast middle history, yet its starting point and its modern pulse rate refuse to connect. This persistent deadlock is precisely what led to the emergence of the secondary crises that are now redefining the discipline. The discovery of the impossible early galaxies by the James Webb Space Telescope has effectively opened a second front in the war against the standard model. For decades, the formation of cosmic structures was believed to be a slow, orderly process governed by the cold dark matter framework. Small fluctuations in the early universe slowly attracted surrounding gas, forming tiny, irregular star clusters that gradually merged over billions of years to create mature spiral and elliptical galaxies. But the deep-field infrared images returning from space are revealing a timeline that looks impossibly condensed. The presence of massive, highly evolved galaxies shining brightly just a few 100 million years after the Big Bang implies that the cosmic engine was running at absolute maximum efficiency from the very first moment. The dilemma this presents to astrophysics is structurally identical to the Hubble tension. It suggests that our fundamental understanding of the rate at which processes occur in the cosmos, whether it is the expansion of space itself or the collapse of matter into stars, is off by a significant margin. To explain how these mature galactic systems could exist so early, scientists are being forced to reconsider the fundamental properties of the primordial gas clouds. Some propose that the early universe possessed highly unusual magnetic fields that accelerated the collapse of matter, while others suggest that the primary generations of stars were vastly more massive than anything observed today, burning through their fuel with blinding, unsustainable intensity to create the bright structures captured by our sensors. As these theoretical battles rage in the preprint servers and university lecture halls, The sheer volume of supporting data confirming the reality of the crisis continues to mount. The S8 tension, the observation that the modern universe is noticeably smoother and less clumpy than it has any right to be, has evolved into a formidable independent challenge to our baseline assumptions. If the Standard Model's inventory of dark matter were perfectly correct, the relentless cumulative pull of gravity over 14 billion years should have crowded matter into dense, highly localized knots and filaments. Yet, when we use the gravitational lensing of billions of background galaxies to map out the real-world distribution of dark matter, the cosmic web looks strangely relaxed, as if some hidden, counteracting force is smoothing out the sharpest peaks of the gravitational landscape. This persistent smoothness has led to the rise of a fascinating field of research known as fuzzy dark matter. Instead of treating dark matter as heavy, localized particles that behave like tiny, invisible billiard balls, this theory suggests that dark matter might be composed of extremely light, ultra-axion particles with an incredibly vast quantum wavelength. Because these particles are so light, their quantum properties manifest on macroscopic galactic scales, creating a natural physical resistance to being squeezed into tight, dense spaces. This quantum pressure would naturally prevent gravity from building the hyperdense structures predicted by the Standard Model, cleanly explaining why the modern cosmos appears far more diffuse and evenly distributed than our traditional computer simulations indicate. The true significance of these overlapping crises is that they are forcing the scientific community to abandon the siloed thinking that often characterizes mature fields of research. For a long time, the scientists studying the Big Bang afterglow, the astronomers measuring local supernovae, and the researchers mapping galaxy clusters could operate in relative isolation, treating their respective domains as independent modules within the broader standard framework. The systemic breakdown of the model has shattered those walls, demonstrating that a change to one component inevitably forces a radical recalculation of all the others. This interconnectedness has transformed the search for a solution into an incredibly high-stakes game of cosmic chess. If a theorist attempts to smooth out the S8 tension by introducing fuzzy dark matter, they must immediately ensure that this quantum pressure doesn't inadvertently prevent the impossible early galaxies from forming in the deep past. If they try to build those early galaxies faster by accelerating gravitational collapse, they risk worsening the smoothness problem in the modern era. The universe has constructed a brilliant locked puzzle box where every piece fits so snugly that changing the shape of a single component threatens to warp the entire structure beyond recognition. It is this profound interconnectedness that brings us back to the stark realization shared by Adam Riess. The solution to this grand cosmological divergence may ultimately require a paradigm shift on par with the transition from Newtonian mechanics to Einsteinian relativity. We are likely not looking at a simple missing ingredient or a minor calibration error. We are looking at a fundamental limitation in the conceptual framework we use to interpret the night sky. Throughout human history, these moments of profound crisis have consistently served as the preludes to our greatest intellectual leaps. When the Ptolemaic system of astronomy, which placed the Earth at the absolute center of the universe, began to encounter stubborn, unexplainable anomalies in the retrograde motions of the planets, astronomers didn't immediately throw away the model. Instead, they spent centuries adding increasingly complex mathematical subcycles called epicycles to the planetary orbits, forcing the broken theory to match the real-world observations through sheer computational brute force. It wasn't until Copernicus, Kepler, and Galileo stepped outside the entire conceptual framework, shifting the center of the system to the sun, that the chaotic complexity of the epicycles dissolved into clean, elegant geometry. We are currently living through the modern equivalent of the epicycle era. Our current efforts to patch the standard model of cosmology, adding early dark energy fields, decaying dark matter particles, and complex modifications to Einstein's gravitational tensors, look suspiciously like the intricate mathematical patches used by ancient astronomers to keep a dying paradigm on life support. We are piling complexity onto our equations to force an incomplete blueprint to match the uncompromising reality of the sky. The ultimate resolution to this crisis will not be decided in the comfort of theoretical isolation. It will be dictated by the cold, impartial verdict of incoming data. The global scientific community is currently mobilizing an astonishing array of ground-based and space-based assets designed to push the boundaries of precision cosmology into entirely uncharted territory. Among the most revolutionary of these upcoming experiments is the deployment of gravitational wave cosmology. Until now, essentially every single measurement of the distance ladder and the cosmic expansion rate has relied on electromagnetic radiation, light waves captured across the spectrum from radio to X-rays. But light is vulnerable to environmental contamination. It can be absorbed by dust, distorted by intergalactic gas, and manipulated by gravitational fields along its journey to our detectors. Gravitational waves, the literal ripples in the fabric of space-time caused by the violent collisions of black holes and neutron stars, suffer from no such limitations. They tear through gas, dust, and entire galaxies completely unimpeded, carrying pristine, uncorrupted geometric information straight from the heart of the cataclysm to our terrestrial interferometers. When a pair of neutron stars collide, they emit both a massive burst of gravitational waves and a simultaneous flash of light known as a kilonova. This dual signature represents the ultimate cosmic target, a siren event. The gravitational wave signal allows physicists to calculate the absolute, unambiguous distance to the collision with pure geometry, completely independent of Cepheid variables, red giants, or any intermediate rungs of the distance ladder. At the same time, the light from the kilonova reveals the exact velocity at which the host galaxy is racing away from us. By capturing a statistically significant sample of these siren events, as our global network of gravitational wave detectors grows more sensitive, astronomy will finally possess a pristine, third independent methodology to adjudicate the Hubble tension once and for all. If the gravitational sirens side with the local distance ladder, the Standard Model's bridge will be definitively shattered. If they side with the Planck satellite, the search for a deeply hidden systematic error in our telescopes will begin anew with fierce intensity. As we wait for these definitive verdicts to clear the fog, the psychological landscape of the discipline remains charged with an undeniable electric energy. The initial defensiveness that greeted the first signs of the Hubble tension has given way to a palpable sense of historical privilege. The scientists working in the field today realize that they are living through one of the exceptionally rare windows in human history, where the map of reality is officially up for rewrite. This is the true beauty of the scientific enterprise. It is a system built entirely on the understanding that our current knowledge is always a working draft, a temporary approximation waiting to be challenged by the next generation of sharper eyes and more precise instruments. The Standard Model of cosmology was not a mistake. It was a magnificent milestone that allowed us to organize our understanding of the universe across vast distances and deep epochs, bringing us to the very edge of the cosmic map. Now, as we stand on that edge looking out into the unexplained discrepancies, the lopsided maps, and the galaxies that built themselves too soon, we are reminded that the universe is far vaster, far stranger, and far more intricate than our most elegant theories could ever anticipate. The cracks found by Adam Riess are not a sign of failure. They are the doors through which the next great generation of human insight will enter. The narrative of a cold, simple, predictable cosmos fading quietly into the dark is giving way to a reality pulsing with hidden dynamics and undiscovered laws. The search remains completely wide open, the tools are sharper than ever, and the sky is waiting for the next genius to arrive and make sense of it all. Settle in, keep looking up, and question absolutely everything. This profound realization that the Standard Model of cosmology is actively fighting against the data marks a significant turning point in the history of science. We are no longer dealing with simple statistical anomalies or minor measurement disagreements. We are witnessing the breakdown of a grand conceptual paradigm. The cosmos is presenting us with a clear structural challenge, and the tools we have used to map the universe for decades are no longer sufficient to explain the reality returning from our finest instruments. To grasp the full magnitude of where this leaves modern physics, it is essential to trace how researchers are attempting to overhaul the very concept of cosmic time and distance. For generations, the foundational assumption of all cosmological tracking has been the principle of homogeneity, the idea that on the largest possible scales, the universe is perfectly uniform, looking essentially the same in every direction and from every vantage point. But as the Hubble tension and its sister crises refuse to dissolve, a small but increasingly vocal group of astrophysicists is questioning whether this foundational assumption is an oversimplification that has blinded us to the true nature of spatial dynamics. What if the universe is not perfectly smooth on macro scales? What if the fabric of space is actually lopsided or organized into immense structural ripples that distort our local measurements? If our cosmic neighborhood sits within a vast, underdense bubble, a cosmic void spanning hundreds of millions of light years, space inside this bubble would naturally expand at a slightly accelerated rate compared to the denser universe outside. The surrounding matter would exert an outward gravitational pull on our local space, artificially inflating the expansion rate registered by our local radar guns. While comprehensive galaxy counts have pushed back against the most extreme versions of this local void hypothesis, the underlying concept remains highly relevant. Our position in the cosmos might not be as thoroughly average as the standard model requires, and the local geometry of space could be introducing environmental distortions that we have failed to properly isolate. This line of questioning has led to the emergence of an entirely new field of study known as inhomogeneous cosmology. Rather than utilizing the standard equations of general relativity applied to a perfectly smooth, idealized universe, these researchers are attempting to solve Einstein's field equations for a cosmos that is inherently fractured, clumpy, and irregular from the very beginning. When you allow for true structural irregularity in the equations, a fascinating mathematical phenomenon known as back reaction occurs. The localized gravitational pull of dense galaxy clusters and the intense expansion of empty cosmic voids begin to actively feed back into the global expansion of space itself. In this framework, the accelerated expansion discovered by Adam Riess doesn't require an exotic, magical dark energy force at all. Instead, the acceleration manifests naturally as a mathematical byproduct of a universe that is becoming increasingly clumpy and disorganized over deep time. The standard model treats the universe as a smooth fluid to make the mathematics trackable on supercomputers, but the real-world cosmos is a chaotic network of dense nodes and immense voids. By smoothing out the wrinkles to make the equations work, we may have accidentally invented dark energy as a phantom force to compensate for the mathematical details we threw away. The complications intensify dramatically when you look at the fundamental properties assigned to the early universe. If the modern expansion rate is truly running faster than the ancient baseline predicts, then the physics operating during the first fraction of a second after the Big Bang must have been vastly more volatile than our current theories allow. This realization has forced a profound reevaluation of the epoch of inflation, that hypothetical moment when the universe blew up from a subatomic point to the size of a galaxy in a microscopic flash of time. In the standard framework, inflation is driven by a simple uniform scalar field called the inflaton. This field is supposed to have rolled down a smooth mathematical potential energy hill, bringing a clean, orderly end to the inflationary expansion and distributing energy evenly across the newborn cosmos. But as the James Webb Space Telescope continues to discover massive, highly organized galaxies existing far too early in history, theorists are being forced to introduce far more chaotic dynamics into the birth of space. What if the inflationary field didn't roll down a smooth hill, but instead cascaded down a jagged, irregular landscape filled with sharp drops and hidden valleys? This multi-field inflation would naturally create massive, highly localized concentrations of matter in the infant universe, primordial hyperdensities that would completely bypass the slow, orderly growth timeline laid out by the standard model. These dense pockets would act as immense gravitational seed crystals, rapidly harvesting surrounding hydrogen gas and igniting into mature, fully structured galactic engines within just a couple 100 million years of the Big Bang. By shifting our understanding of how inflation ended, we can cleanly account for the impossible early galaxies, but we do so by abandoning the clean, predictable symmetry that made the Standard Model so incredibly appealing to a generation of physicists. Theoretical paradigms and their implications. Standard framework assumes a perfectly uniform universe, a static dark energy constant, and a slow bottom-up growth of galaxies. It is highly elegant, but currently failing to match modern precision measurements. Inhomogeneous framework replaces the dark energy force with the mathematical feedback of a clumpy universe. It resolves structural anomalies, but introduces immense computational complexity. Early phase transition framework introduces temporary fields or dark radiation bursts to kick the early expansion rate. It resolves the Hubble tension, but requires inventing new particles that leave no modern trace. The necessity of exploring these highly exotic pathways becomes even more apparent when you examine the profound philosophical crisis currently brewing at the intersection of quantum mechanics and general relativity. As noted previously, when physicists use quantum field theory to calculate the energy density of empty space, the value they arrive at is completely incompatible with real-world observations. This mismatch is not just a localized error, it is a fundamental signpost indicating that our understanding of the vacuum itself is completely broken. In classical physics, a vacuum is treated as absolute nothingness, an empty stage upon which matter and energy perform their cosmic dance. But in the quantum realm, a vacuum is a violent, churning sea of activity. Virtual particles are constantly blinking into existence and annihilating a fraction of a second later, borrowing energy from the vacuum and returning it instantly to the quantum field. According to general relativity, every single one of these virtual particle pairs possesses energy, and because energy equals mass, every single one of these quantum fluctuations must exert a gravitational pull. If you add up the collective gravitational influence of all the virtual particles popping in and out of existence throughout the cosmos, the universe should be expanding so violently fast that entire atoms would be ripped apart before they could ever bind together to form a single star. The fact that the universe exists at all means there must be some deeply hidden, perfectly calibrated cancellation mechanism at play. A law of nature we have completely failed to discover that cancels out 119 orders of magnitude of quantum energy, leaving behind only the tiny, subtle outward push we identify as dark energy. When Adam Riess clocks the modern expansion rate at a value 9% faster than expected, he is not just measuring the movement of galaxies, he is probing the microscopic residual leftovers of this immense quantum cancellation. The Hubble tension is the macroscopic fingerprint of a quantum mystery that we lack the theoretical tools to decipher. As this theoretical gridlock persists, the socio-political dynamics within the scientific community are becoming increasingly charged. For decades, cosmology operated as a field where the overarching narrative was entirely secure, and the primary work consisted of refining the parameters of that narrative. This created a highly specific academic ecosystem where young researchers were heavily incentivized to build their careers within the safe, established boundaries of the standard framework. The sudden empirical validation of the Hubble tension has completely upended this hierarchy. It has created a profound generation gap within university physics departments around the world. Older, established tenure-track professors who spent 30 years polishing the mathematical details of the standard model are naturally inclined to defend the framework, searching desperately for systematic errors in the data or instrument calibrations that might save their life's work. Meanwhile, a younger generation of postdocs and graduate students looks at the cracks in the windshield, not with anxiety, but with immense excitement. They recognize that the standard model is an aging fortress, and that the reputation of the next great generation of physicists will be forged by those who have the courage to tear down the broken walls and build something entirely new in their place. This generational shift is exactly why the ongoing work of Adam Riess is so uniquely profound. He bridges the gap between these two worlds. He isn't a young iconoclast trying to make a name for himself by attacking the establishment. He is the establishment. Yet his absolute loyalty to the integrity of empirical data has forced him to become the chief investigator of the very model that brought him his greatest professional triumph. The true test of which camp holds the map to reality will ultimately be decided by the sheer volume of new data currently rushing toward the scientific community. The mid to late 2020s are delivering a series of critical empirical checkpoints that will strip away the remaining ambiguities and force a definitive resolution to the crisis. One of the most vital new tools currently coming online is the next generation of cosmic microwave background polarimeters, operating from high-altitude desert plateaus in Chile and the frozen expanses of the South Pole. These highly sensitive instruments are designed to map not just the temperature variations in the Big Bang afterglow, but the precise polarization patterns, the physical orientation of the light waves as they scattered off the primordial plasma. By measuring these polarization fields with unprecedented fidelity, scientists can execute an entirely independent audit of the ancient universe parameters. They can determine with absolute certainty whether the lower expansion rate calculated by the Planck satellite is an unshakable reality of the early cosmos, or whether some subtle, unmapped, systematic distortion has corrupted our interpretation of the temperature speckles. If the polarization data confirms the lower number, the escape route for defenders of the Standard Model will be permanently closed, leaving a broken bridge as the only logical conclusion. Concurrently, the deployment of fast radio burst cosmology is providing a radically new methodology for mapping the intermediate universe. Fast radio bursts, FRBs, are incredibly intense, millisecond-long flashes of radio light originating from highly magnetic neutron stars located billions of light years away. As these powerful radio signals travel across the intergalactic void to reach our terrestrial radio telescopes, they interact directly with the sparse, invisible sea of free electrons scattered throughout the cosmos. This interaction causes a highly predictable physical effect known as dispersion, where higher frequency radio waves arrive at our detectors a fraction of a second ahead of lower frequency waves. By measuring the precise degree of this dispersion across thousands of independent radio bursts at varying distances, astronomers can construct a high-fidelity continuous inventory of every single electron sitting in the space between galaxies. This electron map provides a direct, uncorrupted measure of the total density of ordinary matter in the universe, completely independent of the assumptions used in the Standard Model. If the matter density returned by the radio bursts aligns with the smoother, more diffuse parameters indicated by the S8 tension, it will confirm that the modern cosmos is genuinely less clumpy than our traditional gravity equations demand, providing crucial support for exotic frameworks like fuzzy dark matter or dynamic dark energy fields. As these independent lines of evidence converge, the scientific community is being forced to confront a deeply moving realization about the nature of space and time. For centuries, our picture of the universe has steadily expanded, moving from a small, Earth-centered system of elegant crystal spheres to a vast, cold, indifferent expanse of accelerating space dominated by invisible dark components. With each step forward, human certainty has been challenged, and our comfortable assumptions have been systematically dismantled by the uncompromising reality of the night sky. The current crisis in cosmology is not an operational failure. It is the natural, inevitable outcome of a system that is functioning exactly as it was designed to. We have pushed our observational capabilities to such an absolute peak of precision that the universe can no longer hide its remaining secrets behind a wall of blurry data or statistical noise. The cracks running through the core of our master blueprint are the literal pathways to our next great intellectual leap forward. We are living through the final days of an old consensus and the turbulent, chaotic birth of a new worldview. The story of a simple, uniform universe born in a pristine flash, held together by inert, invisible matter, and destined for a clean, predictable fade into the dark, is giving way to a reality that is vastly more dynamic, complex, and deeply mysterious than anything we have ever written into our textbooks. The distance ladder is true, the ancient pulse is real, the bridge between them is broken, and the search for the next grand synthesis of human knowledge remains completely wide open. Settle in, look up into the dark, and be ready to rewrite everything you thought you knew. The physical confirmation that our universe is defying the standard blueprint has triggered a quiet urgency within the walls of the world's most prestigious physics departments. We have arrived at a crossroads where data is no longer the servant of theory, but its absolute master. The structural cracks first uncovered by Adam Riess are no longer isolated mathematical anomalies. They have formed a continuous, expanding fault line across the entire landscape of modern astrophysics. To grasp the full weight of this paradigm shift, one must look at how researchers are forced to re-examine the conceptual framework of cosmic acceleration itself. In the standard paradigm, the acceleration is treated as a smooth, isotropic phenomenon, meaning it pushes outward with absolute equality in every direction, treating every patch of the sky with the same uniform pressure. But as the precision of our distance ladder climbs to unprecedented heights, a deeply unsettling possibility has emerged from the data. What if the expansion of the universe is lopsided? This concept, known as cosmic anisotropy, suggests that the repulsive push of dark energy might not be a uniform background hum, but a directional force that varies depending on where you aim your telescopes. Astronomers mapping the movement of thousands of distant galaxy clusters have noticed strange, unaccountable drifts, massive structural migrations across the cosmic web that look less like random local motion and more like a collective slide toward a specific hemisphere of the sky. If dark energy is stronger in one direction than another, it implies that the universe possesses a fundamental preferred axis, a cosmic orientation that shatters the Copernican principle of perfect uniformity. The standard model simplifies the mathematics by assuming space has no favorite direction. But the real-world cosmos may be inherently asymmetrical, pulling itself apart with a structural bias that our current equations are completely unequipped to calculate. This potential asymmetry has breathed new life into an exotic branch of physics known as tensor vector scalar, TVS, gravitational theories. Rather than treating gravity as a simple geometric curvature described by a single metric tensor, these radical frameworks introduce entirely new vector fields that permeate the vacuum of space. These hidden vector fields act as a sort of invisible fluid dynamic flowing through the expanding cosmos and interacting with the distribution of dark matter over deep time. In this scenario, the directional anomalies we see in the expansion rate are not errors in our distance rungs, but the physical manifestations of this vector field interacting with the massive filaments of the cosmic web. The field would naturally create localized channels of accelerated expansion, allowing space to stretch faster along specific cosmic corridors while remaining standard and predictable in others. By abandoning the strict simplicity of a single gravitational tensor, we can neatly reconcile the conflicting measurements of the Hubble constant, but we do so by opening a Pandora's box of mathematical complexity that threatens to make our supercomputer simulations of the early universe completely untractable. The necessity of exploring these highly intricate pathways becomes even more apparent when you look at the profound crisis currently brewing within the study of primordial nucleosynthesis. This is the highly specialized branch of astrophysics that maps out the precise chemical element production that occurred during the first 3 minutes of cosmic history. For decades, the standard model's account of this era was considered an ironclad triumph, predicting the exact ratios of hydrogen, helium, and lithium that should have been cooked up in the Big Bang furnace. But as our spectroscopic instruments have grown sharp enough to analyze the pristine, unpolluted gas clouds floating in the deepest intergalactic voids, a glaring discrepancy has hardened into a permalum, the cosmic lithium problem. Our finest models of the early universe predict that there should be roughly 3 times more lithium-7 in the cosmos than we actually observe when we look at the oldest, most metal-poor stars in the galaxy. Primordial element distribution discrepancy. Hydrogen 1. Theoretical prediction and real-world observations match with near-flawless precision. Helium 4. Observational metrics align cleanly with the calculated output of the primordial furnace. Lithium 7. Real-world measurements reveal only about 1/3 of the total lithium demanded by the standard framework. For a long time, astronomers hoped this missing lithium was simply a local anomaly. that the ancient stars had somehow absorbed or destroyed the element within their internal nuclear cores over time. But as the Hubble tension and the S8 tension have demonstrated that our model's bridge between the past and present is broken, scientists are beginning to wonder if the lithium deficit is another systemic clue. If the early universe experienced a brief volatile phase transition that altered the expansion rate during the first 3 minutes, it would naturally disrupt the nuclear reaction rates, suppressing the production of lithium while leaving hydrogen and helium relatively untouched. The lithium problem and the expansion rate crisis may be two distinct symptoms of the exact same hidden physical mechanism operating at the very dawn of time. This deep-seated interconnectedness is precisely what makes the current state of modern cosmology so uniquely compelling. The field has evolved beyond the point where a single creative theoretical paper can save the day. Every time a physicist adjusts an equation to smooth out the S8 tension, those modifications inevitably ripple through the history of the cosmos, throwing the beautiful alignment of the cosmic microwave background or the rigid checkpoints of baryon acoustic oscillations into complete disarray. The universe has constructed an incredibly tightly locked puzzle box. If a researcher introduces an early dark energy field to kick the expansion rate forward before the creation of the baby picture, that temporary surge of energy alters the sound speed of the primordial plasma. This, in turn, shifts the physical scale of the frozen sound horizons, causing the predicted positions of modern galaxy rings to drift completely away from the real-world positions mapped by our robotic sky surveys. The data has become so incredibly dense and precise that there is simply no longer any comfortable rug under which scientists can sweep their theoretical garbage. The model is forced to perform perfectly across every single epoch simultaneously, and its failure to do so is a clear message that we are missing a fundamental law of physics. The response to this gathering storm within the global scientific community has been marked by a fascinating mixture of intellectual humility and relentless empirical tracking. The initial skepticism that greeted the first hints of the Hubble tension has transformed into a profound respect for the integrity of the data. Scientists realize that the discrepancies are no longer going to dissolve with better instruments. The best instruments ever built have walked into the room and certified the crisis. This has led to the rapid acceleration of the dark energy survey and the deployment of massive deep sky mapping initiatives that are capturing millions of new cosmic data points every single week. Instead of relying on a handful of standard candles or isolated galaxy clusters, astronomers are utilizing advanced artificial intelligence algorithms to process vast petabyte-scale deep sky surveys, mapping the exact movements, shapes, and distances of billions of galaxies across the observable horizon. This transition to automated hyperscale astronomy represents a fundamental shift in how human beings interact with the night sky. We are no longer lone observers peering through a glass lens, trying to infer the architecture of the cosmos from a few dozen data points. We are building a high-definition, multi-dimensional digital twin of the entire universe, allowing the collective movements of the stars to expose the limits of our theories through sheer statistical weight. As we look toward the immediate future, the definitive resolution to this great cosmological divergence is converging on a series of highly anticipated operational checkpoints. The coming years will see the full operational integration of the Vera C. Rubin Observatory in Chile and the launch of the Nancy Grace Roman Space Telescope. These next-generation systems are explicitly engineered to look past the superficial features of the modern universe and peer directly into the deep mechanics of the invisible dark empire. The Rubin Observatory, with its massive 3-gigapixel camera, will execute an unyielding 10-year time-lapse movie of the changing sky, tracking the evolution of dark matter scaffolding across deep time with unprecedented fidelity. At the same time, the Roman Space Telescope will deploy its high-precision infrared sensors to capture thousands of new, ultra-distant Type 1a supernovae, rebuilding the cosmic distance ladder with a level of statistical control that will leave absolutely no room for lingering debates about dust, chemistry, or stellar crowding. If these incoming datasets confirm that the modern expansion rate remains fast, While the smoother distribution of matter indicated by the S8 tension holds firm, the Standard Model's reign will officially draw to a close. The scientific community will be forced to set aside the comfortable textbook assumptions that governed cosmology for a generation and begin the difficult, exhilarating work of drafting a completely new blueprint for the universe. We stand in the shadow of a genuine intellectual revolution. The cracks running through the foundation of our master blueprint are not a sign of failure, but a profound testament to how far human curiosity has carried us. We have pushed our understanding to the absolute edge of the map, and the universe has responded by showing us that its true architecture is vastly more dynamic, complex, and beautiful than anything we ever anticipated. The distance ladder holds true. The ancient pulse stands firm, the bridge between them is broken, and the horizon remains completely wide open. Settle in, keep your eyes fixed on the deep dark, and be ready to question absolutely everything you know.